you guys open up RStudio, does it open up the last thing that you were working on, even on these computers?
Well, it opens up like the startup page, and they're in like one tab, and then another tab that has something like that.
Okay, then it has what you were working on.
It's too scary.
Figure out where that option. Mine opens up. Move things over so you can see some different options. All right, so let's see here. Global options is under tools. All right, and then you've got different stuff that you can use. So debugging, OS integration. You can leave everything as is. So under workspace, I have restore.r data into workspace at startup. All right, so the R data is the workspace. If you go to tools and option, global options, see if that's checked. Is that checked for you? It is. All right, just say always save history. Yeah. Oh, and then there's this checkbox. Restore most recently opened project at startup. Are all those checked? Tools and global options. So tools and global options. Normally that's where it's at. Check the advanced. So you got edits for the code. Display. Saving. We've got completion check. So everyone probably says that. Let's see, R diagnostics. Here's your appearance. So I don't know if you want to mess with that. Mine's on modern. But there's a classic look apparently, and there's a sky look. Don't know what the difference is. But the editor. Let's see what I'm on. I'm on TextMate, which is the default. If you go through here, you can see that there are different ways to show the editor. So it depends on what you like. I typically have like a dark theme. Sometimes I think the colors are hard to see. Like purple on a black background, really hard for me to see. Here, I mean, it kind of looks okay, but sometimes that magenta just looks awful. But you can kind of play around with that, mess around. The page layout, you can kind of change where you put things. And what's included. So if I don't need this VCS, I can uncheck it and it just won't appear anymore. Packages, specify it kind of where you put everything, or the defaults or anyway. Markdown, let's see here. Yeah, so I'm gonna guess that. I mean, as long as you had those open, I think this is where mine is. So if this was unchecked, when I open up RStudio, it's just blank. There is a possibility that it's saving it to your user folder, but it's saving it on the hard drive. So when you log out, these computers have like a deep freeze function that'll delete anything that's in there, so that anyone who logs back in is going to get a fresh computer. And the idea is that they don't want Alex in here to plug in some sort of virus onto this computer and have it spread. So when he logs out, it just completely wipes that hard drive, in theory. My bet is that some hackers out there are trying to figure out, or have already figured out how to get around that. So I don't know what else we can do. And the reason I say that is because I found this, where it talked about how to restore closed, unsaved scripts in RStudio. So if you're in Windows, you go to this location. So users, so C:users, whatever the username is, app data local. So all of this is stored on the C drive, and I think this is the folders that get wiped every time you log out and log back in, I believe. All right. Not sure. Yeah, so read this. So this popped up in the news. All right. So if you actually read the story, a group of epidemiologists early part of July actually wrote a letter and said that you have all the evidence. If you go back even farther back, so end of January, early February, you already had the epidemiologists saying, look, this is not spread by picking it up off of desks and touching your face. It's just not how it works. The rated speed at which it's transmitting to people suggests that it's aerosol transmission. There are people putting that out for a while, and this is more of a lengthy article. It's nice to see this actually get picked up in more of the major news articles, because it really is saying, look, that respiratory droplets, while they may play a role, it's going to be a smaller role. This cleaning off the desk nonsense, I mean, it's just, that's so unlikely that it's actually playing a major role that we should be focusing on other things like aerosol transmission, and they kind of go through it. So if you read the story, they mentioned it was in July 9th. I mean, it was early July, and they had a letter. These guys signed a letter and made a bunch of arguments, and these aren't just fly-by-night people. I mean, these are people that actually study disease transmission. They're saying, look, everything's being said isn't quite right. So you could ask, why is that? Why hasn't the CDC or the World Health Organization admitted that? Best thing I can say is that the CDC and the World Health Organization isn't just about putting out science. It's also about managing people. So if you told people back at the end of January that this thing spreads through the air, imagine what the public response would be. Just imagine. I can think of worst case scenario. Look to the movies. Think of I think Contagion. Think of World War Z. I mean, people are gonna panic.
Oh, there's a one. Have you seen 12 Monkeys?
I haven't seen that one.
Yeah, that's like a.
I mean, you can just say, you think of people who respond, they're going to hear it, it spread through the air, and oh my goodness. I mean, you think toilet paper shortages were bad, thinking air filter shortages are going to be bad, oxygen tanks are going to be bad. I mean, you're going to see people walking around with their own air. I mean, that's the overreaction. So, it's not just about, these organizations they're not only about showing the science, they also have to think about what is going to be the public response to it, because people are irrational when it comes to a lot of this stuff. But this popped up in the news. It's biology related. It's kind of interesting to actually read through it. If you want, just do aerosol transmission, and it's Time Magazine put it out. So it is somewhat of a lengthy article, but they do talk about what we kind of should be doing.
Do they still suggest wearing masks?
They do, but the masks should be more tight-fitting than what these currently are. Like, I know that, I can feel the air kind of moving out.
Yes.
Yeah, so in the article, it's like, okay, don't walk behind somebody with a poor-fitting mask, because as they breathe, they're putting out the aerosol, behind them, and check it out. So I do like to do, stuff in the news. I was going to bring up a stats thing that was in the news, and I think it was related to, hydroxychloroquine and azithromycin, and their sample size was like 95,000 people. And at that sample size, you'll get a significant p-value if the difference is like 0.1% difference. I mean, it's huge. So I didn't actually find the paper yet, but when I do, we'll look at that, because that's something that we talk about is, sample size affects the test, power of the test. It affects the likelihood that we'll actually find significance, but we always have to go back and look at that significance and say, yes, okay, so statistically we did find a good p-value, but is it biologically meaningful? Increasing your chance of death by 0.01%, while we could get a p-value that's significant, is that really meaningful? You can increase that chance of death just by walking to school more, because you have to walk across the street a few more times. There's a lot of things like that. So we'll talk about a lot of that stuff moving forward. So in the meantime, how was the homework assignment? Is it going okay? All right, so a couple things, and I'm gonna put this up. So I do think this presentation is posted on Blackboard. All right, practicing data import in R. This would have been the natural progression. So I think what we had done in the past is we had made it through the R stuff. All right, made it through that last lecture, and then in the lab component, we did practicing data import in R, which kind of told you a little bit more about the folder structure that I talked about. Having this word template in the correct place, which we've already gone over. But now I kind of go on how to get the Excel, how to enter data into Excel, how to get it into CSV file and import it. Now, we don't have to spend an entire class, because some of you probably already know how to save as in Excel and change it to a CSV and import it. All right. So I did have this R data import practice.rmd file that kind of steps you through how to do some stuff. So I'm going to say you can do it on your own time if you want a little bit more practice. But I think if you work through the homework, it's probably going to be okay. So it's things like you take this data set, something that you would have collected. How do we get that into R? Well, recommendation is to put it in an Excel first and then save it as a CSV and transfer it over. Same thing, here's the second data frame. Sometimes the data is going to be set up like this, where you've got IDs and you've got left and right measurements. How do we get these measurements into R? All right, and then I introduce some functions. All right, and we're going to do these more. All right, but table that creates a frequency table, and that's one way in which we can check to make sure that our data were read incorrectly. Histograms. I think we had hist in this homework assignment, where I just basically said, use this hist. Here's the function. I didn't explain what it was doing a whole lot. It was just a check to make sure that you had your data in R correctly. And it's something that we'll go over in more depth. All right, and then kind of practice this word file, doing the markdown stuff, and we did do that. We tried it with our notes, and then when you try it on your homework, you just got to remember that word template has to be called word template, has to be in the same folder that you save that RMD file. All right, so I believe this is posted. If you want to work through it on your own time, you can. I don't think you really need to do it, because I think most people were getting the hang of R Studio and the Markdown documents. If you run into errors, please email me. All right. Now let's move on. We'll take a slight break from R. We're going to take a slight break from R. We're going to get back to introducing you to stats. There is going to be some R stuff that's in here, all right, but it's not going to be terribly difficult. All right, so what we're going to do is move into data in biology. Now, in that open stats book, this is chapters 1 and 2. This is kind of going over, the data types, some of the definitions used in statistics. Of all of these things, the concepts are what's important. and we're going to hopefully drill it down so that you know it. The variable types, you have to be able to identify the variables and their types. So what type of variable, what's their scale, because it's that information that tells us what type of statistical test we can perform. All right, so statistics and probability, these are basically the two main fields that are there in statistics. So collection, so in statistics, we utilize probability theory to come up with predictions, to come up with comparisons, to try to figure out if data are different. Now, in statistics, we have two main fields that we can look at. We can do a descriptive statistics field or inferential statistics. They are not mutually exclusive, all right? If you're doing inferential statistics, you're also going to be doing some of the descriptive statistics. All right, if you do descriptive statistics, you might not do the inferential statistics, but you probably are. All right, so descriptive statistics is all about organizing and summarizing data. All right, that's including getting your numerical summaries, so calculating means, medians, variances, and it's also generating visual summaries. So visualizing your data, which would be your making the graphs and making the figures. Inferential statistics is when we try to draw conclusions from the data. All right, so descriptive statistics is just doing your basic summaries, means, medians, variances. The inferential statistics tries to take those numbers and make conclusions. So if I were to repeat this study, how likely is it that I would get the same mean or the same variance and so forth? All right, with the inferential statistics, we are going to assign confidence values to our estimates, to our predictions. The higher the confidence, the more likely it is that our predictions will be correct. All right, the lower the confidence, the more likely that our predictions will be wrong. But I do put these statements in parentheses that say, okay, yeah, if we have low confidence, we could be wrong, but on the flip side, we could be right. All right, we could be right a small percentage of time. If we have high confidence, yeah, our conclusions are probably correct, but they could also be wrong. And this is our error that we can talk about. We have different types of error that we have to try to avoid to minimize these situations where we're wrong in our predictions. Our predictions say one thing, we want to have as high of confidence in those predictions as possible. All right. Now, our inferential statistics relies on probability theory. What's probability? It's the likelihood that an event will occur. It's a likelihood that an event will occur. All right, so example was Carl Pearson. We talked about him. He introduced a lot of different stuff with stats and statistics. He flipped a coin 24,000 times to come up with a binomial distribution. Can you imagine? 24,000 times. In that 24,000 times, he flipped 12,012 heads. 12,012 heads. Some of this was, I think, just the heads part was cut off on our feed. Almost 50%. I mean, almost 50%. 50% is 12,000 exactly. Right? It's pretty darn close out of 24,000. So our probability of flipping heads is 50%. Every time we flip a coin, we have 50% chance that it turns out to be heads. All right, so with our statistics, we're going to be working with samples and populations. All right. So normally, we collect samples and we make predictions about the population itself. So what is our population? Our population is the universe. It's all possible values that you can obtain. It's all possible data, sample items. It's all possible individuals that are out there that we could have collected data on. All right. So the real definition, or I should say the textbook definition, is the totality of individual observations about which inferences are to be made, existing anywhere in the world, or at least within a definitely specified sampling area, limited in space and time. All right. So we can set up boundaries with this population. All right.
It's just going to be the totality of all of our observations that we could make, all right, and we can define it to represent only those items in a single room, or a building, or a town, or a state, and so forth, all right? So we can define what our population it is in. It is this group that we're trying to make conclusions about, all right? It's this group that we're trying to make conclusions about. So how we approach it is we're going to take a sample, which is a subset of that population. From that subset, then, all of our statistics could represent the statistics that we see in our population. Statistics, in that case, isn't quite right. So our samples give us a statistic that should match the parameters in our population. All right, so the group that we're interested in specifies a sampling regime. So as I said, we can define our population based on areas. So if we're interested in the roaches that are here in this building, all right, we can define that population is only the roaches in cabinets. But perhaps we wanted to look at the roaches all across campus. Then our population only includes those roaches here on ASU's campus. Perhaps we wanted to look at all the roaches in San Angelo. There's our definition. Or all the roaches in Texas. There's our population. All right. Now, with our population, we can be individuals, or we can refer to individuals, which is what I kind of did with the roaches, or it could be experiments. So you've all had classes where they emphasize you should repeat your experiment. You should repeat your experiment over and over and over again. Well, our population of experiments is all the experiments that we could do, we could perform, if we had unlimited time and resources. But we don't have unlimited time and resources, so we do a sample of these experiments and hope that our sample of experiments actually represent the population of experiments that we couldn't actually perform. All right? So I'm going to note well here that most of our populations are finite. All right? Most of our populations are finite. There's only a certain number of roaches that live in this building. Might be a lot of them. There's only a certain number of them. But when it comes to probability theory, we assume that that population size is infinitely large. Why is that? Well, let's think about, a just regular basic probability. Right? We have, let's say, the daily lottery. You've got a container that has balls from numbered 0 to 9. All right. What's the probability of drawing a 5? Reaching in and grabbing the ball that's marked number 5. 10 balls? Yeah, 1 out of 10, right? 10%. Don't shake your head, Cody. We're going to learn. We'll get it. We'll get it. All right, so 1 out of 10. All right, so that was one sample. But we're going to reach in and pull out a second ball. And now I ask you, what's the probability of drawing a 6?
Did you put the 5 back?
That's what matters. Did we put the ball back? If we assume that the population is infinitely large, it doesn't even matter. That ball that we took out, the sample size, was reduced by 1, but going from 1,000,000 to 999,999 items isn't going to change our probability. But going from 10 balls down to 9 balls, 10% down to 1/9, which is more than 10%. All right? So in practice, even though our populations are finite, we assume that they are infinite. And when we work with populations, all of the numerical descriptors are called parameters. So means, medians, variances, those are all things that we can calculate for a population. But now those values, they're not called statistics anymore. They're called parameters. They define our population. All right, so it's unlikely that we're going to be able to sample every single individual or object in our population or do every single experiment that we want. So what we're going to do is use samples to represent our population. So how we take the sample is through a process called random sampling. Random sampling is when we take a sample and every single item in that sample was obtained at the same frequency as all of those same items in our population. So we have the same probability of drawing any individual that's out there. And then when we have our total sample together, the distribution of items in our sample reflects that of a population. Textbook definition The frequencies within the sample equal to the true frequencies in the population. So each item in our population has the same probability of being drawn, but as we put together our sample, the underlying distributions match the population. All right, if we have a random sample, then we should have a representative sample. Example of this is it goes to what's in the news. You can say is that you look at the vaccine trials for the coronavirus. All right, you've probably seen that some of these trials people are complaining because the volunteers, the sample of individuals that are going through that vaccine trial, doesn't necessarily match the ethnic distribution across our population. All right. So if our sample actually is a random sample, then we look at distribution, so you can say race in our population, and say, okay, if we have 60% Caucasians in our population, then our sample should have 60% Caucasians. If we have 30% African American, we should have 30% African American in our samples. In those vaccine studies, that's not the case. They try, but you have underrepresentation of some groups, overrepresentation of other groups. It's not technically a random sample.
Volunteer-based stuff?
A lot of it is volunteer. But here we can do an experiment. We can do an experiment. Let's say somebody here wants to do their honors project or their grad project on views of different subjects. All right. So you say, I want to know a student's views on science, English, history, and psychology. All right, because you think that everyone's going to have a low view of psychology because it's not a real science. Just joking. Just joking. I don't know. Is anyone here a psychology major? Anyone?
Well, at least you feel
I've
better
had
about
one.
that college.
I've had. Well,
Oh,
I've
you've
had-
had psychology?
we have it. Yeah. Got one student. We go on and on about it. So you can ask. You need a random sample. What good does it do you to stand at the entrance of cabinets and ask those students? Chances are you're going to get students that are coming here to take a science class, and you're probably going to oversample your biology majors. I don't think there's many psychology classes that are here in this building. If you go, I think psychology is over in the academic part. Academic,
Academic, yeah.
right? So if you go on the steps of the academic building, you're going to oversample students that mostly have classes over there. If you go stand out at the Fine Arts Center, right, you're going to get a completely different answer. All right, so same type of deal. Sometimes our sampling regime doesn't give us the random sample that we're looking for, and we have to be careful with that. All right, but our focus is always to try to get a random sample. If we get a random sample, then in theory, our sample statistics, so those means, variances, standard deviations, everything that we calculate from our sample should match the population parameters if we have a random sample. So how do we get our random samples? All right, how do we get our random samples? Well, we have two methods of collecting our random samples. All right, and our methods kind of depend on what we define as a population. All right, so the first time is if we know the entire population, if we know and can mark every single individual in our population, then what we can do is assign numbers to them and then just have the computer randomly draw a collection of numbers, and those are the numbers that we measure. So let's say we go out to a forest. All right, there's, let's say, 1,000 trees in the forest, and you're going to go do a procedure that doesn't allow you to actually go out and do all 1,000. Maybe you can only do 25 trees. Well, you number each tree 1 to 1,000, and then what you do is randomly sample 25 of those numbers, and those are the trees that you then go out and actually take your data on. All right, so that's method number one. If we don't know the entire population, then we've got, again, kind of depends on what kind of analysis we're doing, but what we want is to randomly select our collection points via computer and then possibly establish grids. So in our forest, maybe we can't count every single individual. So now we look at a map, we have a computer pick 25 points on that map, and then when we go out to those points, we have this procedure where we set out, a grid, or perhaps we say we're going to take the closest tree that is to the north of that point. All right? Our random sample was generated by these collection points. Another way we can do it is to pick a random point and then just walk randomly in a direction. So you say, I'm going to walk for 10 feet and I'm going to sample every plant that I find. Once I get to the end of 10 feet, I take a spinner and I spin it, and whichever direction it points, that's the next direction in which I walk, and so forth. So what we're doing is just randomizing where we're collecting all of our points. And then if you have different types of experiments and you're trying to figure out which gives you the best random sample procedures, you can always ask me. All right. Now there is something behind this image, behind my screen on this live feed, but if you download and check out the presentation, I have a green box here. I'm speaking to the YouTube audience here. So our ability to do good stats depends on how we sample the population, and that is hugely important. So our ability to do good stats depends on how we sample the population. If we only sample, let's say, one type of tree, big and old trees, we can't apply the information obtained from those trees to the new growth. It just doesn't happen. We can't do that. We don't have a representative sample. All right, so our random samples consist of observations. There are two types of observations. All right? There's an individual observation and there's a sample of observation. Unfortunately, they use the same terms. All right? Individual observations is basically the data point. That's our single item where we collect our data. All right, so the individual observation or measurement taken on our smallest sampling unit. The sample of observation is a collection of individual observations selected by a specific procedure. So you take your individual observation, you repeat that on individuals in your sample, and now you have a sample of observation. To ease this distinction, we're going to talk about the individual sample or our data point. And then when we talk about a sample, I'm referring to all of those data points that we have for that sample. All right. Also data set, also data. All right. And so forth. So example here. We take our roaches. All right. We measure wing lengths on the roaches. All right. Each roach gives us a wing length. So the wing length for a single roach, that's our single data point. That's our individual observation. Say we measured 50 roaches. Those 50 measurements then represent our sample, our data set, or our data. All right. Smallest sampling unit. Our smallest sampling unit is actually on our roach. All right? It's not the wing. Because we can take that roach and we can measure the other wing. We can measure the legs and so forth. So our smallest sampling unit is the individual itself, but then that individual could generate different data points. Why is this important? It's something called independence. All right, and it's going to be a very important assumption for all of our statistics. Almost all of the tests that we run assume that our data points are independent of each other. But if you measure wing length and leg length and then try to analyze them, well, on the individual, you assume a large roach should have a large wing length and large leg length. Those two measurements are not independent of each other because it came down to our smallest sampling unit. We'll mention that. You'll hear me talk about it. We'll give a few more examples. But for us, our distinctions between our data point and the sample. Individual observation versus individual sample. Or sample of observation. All right, so variables. Variable is a character. That's what was measured. This is the actual property that was measured by our individual observation. So for our roaches, it was wing length. That was our variable. All right. That variable is going to represent a single column in R and in Excel. It's a typical data set in R. One variable, one column. And then I also note that more than one variable can come from the smallest sampling unit. And that's important because our smallest sampling unit represents the rows of our data set. So our rows represent the sampling unit, our variables represent the columns. And I do think we went over this, implications of the smallest sampling unit. If one variable is taken on each sampling unit, we're good to go. no violation of our assumptions. But if more than one variable is sampled on each sampling units, then our variables are not independent. So if we took leaves and we measured the lengths and the width and the width are not independent of each other. They're not independent of each other. If we have that case, then we can study, what we're actually studying is a bivariate sample, which is paired observations on the smallest sampling unit. We'll see it. So here's our relationship between samples and populations. All right, so our populations consist of parameters. It's defined by parameters. They're going to have means, our mu, our standard deviation, sigma, our rho is proportions, d is differences, pi, let's see here, no, rho is correlations, pi is proportions, the delta is differences. All right, so all of our population parameters take on Greek letters. All right, from this population, we are going to have a smaller sample that we then can calculate all of the same types of values. So our bars, x bar, y bars, z bars, all right, our averages. S is our standard deviation, R is our correlation, D is our difference, P is our proportions. All right? We use these to make inferences about our population. If we have a random sample, then these values should be equal. If we have a random sample. Not all of them will be exactly equal. We have a term called bias. Some of our parameters or some of our sample statistics are biased. They will actually underestimate the population parameter. By point, we use our sample statistics to make inferences about our population parameters. All right, you good? All right, variables in biology. So our goal, anytime we work with variables, is to pick one whose properties vary in some measurable way. All right, we want to be able to measure it. Not only measure it, we have to first detect it, and then we have to measure it. All right. So with our variables, we have two types of variables that we can choose. We have our qualitative variables, and we have our quantitative variables. Our qualitative variables are all of those variables that are non-numeric data, and they're expressed using their attributes. Examples: hair color, sex, nationality. Right? Those are just inherently, they're non-numeric, but they have attributes, and they're classified. Right? Variable types that are qualitative include categorical variables and nominal variables. Basically mean the same thing. Right? We refer to their attributes, their categories. When working with qualitative data, we often present those data in combinations with frequencies, usually expressed in frequency or enumeration tables or bar graphs. So we can say what the sex ratio is, the percentage of male, percentage of female. We can talk about the percentage of individuals with brown hair or black hair or blonde hair. We can talk about percentage of individuals from different countries and so forth. All right, we represent this as frequencies, percentages. The second variable type is quantitative. All right, they can be expressed numerically, or they are expressed numerically, and they consist of two general types, specific types. One is continuous variables, and the other is discrete variables. I'll start with discrete variables. Discrete variables are those numeric data whose values are confined to whole numbers. All right. Definition is that they're limited to a specific state with no intermediate values possible. It's typically whole numbers. Yep.
So like how many kids they have?
Yep, you can't have a half a kid, right? You can't have a half a kid or 3/4 of a kid. Some people might think they have half a kid. All right. They don't. It's a whole kid. All right. So yeah, discrete variables, they're limited to specific states. No intermediates are possible. All right. These are also called discontinuous or meristic variables. You may encounter them. I'll probably just always call them discrete variables. Right? Whereas with like our qualitative, you'll hear me call them categorical and nominal interchangeably. Discrete variables, I almost always use discrete variables. All right, so yeah, how many leaves are on a tree, or how many tomatoes were produced by a plant? You can't have half tomatoes. You can't have half of a leaf. Yeah, you can have an herbivore come over and eat half of a leaf, but it still didn't change the fact that there was a leaf there. It's whole numbers. All right. The other one is continuous variables. Now, continuous variables can take any value within two fixed points. All right, we're not confined to only whole numbers. We can take any value, which means we have an infinite number of possibilities. Now, if we do our leaf area, all right, we can have, or we're bounded by 0, so actually it can't be defined by 0. You can't have 0 area. You don't have a leaf. All right? But you can have, let's say, a leaf surface area of 100 square centimeters. You can have a surface area of 100.1 square centimeters. 100.01, 0.0001, 100.00000 out to 105, zeros, 1, and then a 1 at the end. All right, that's our infinite number of possibilities. If I ask you, what's the probability of getting a leaf area of 100 square centimeters? Your probability is actually going to be pretty damn close to 0 because you have an infinite number of possibilities. But if we say, okay, we'll allow you to round, now what's the probability? Oh, now it's a whole lot better. Now it's much higher because we've rounded. All right, so yeah, that's what I said. We can have many repeats with these continuous variables, happens for rounding. So don't look at a data set and say, well, I've got repeats, so it must not be a continuous variable. No, we've rounded. In reality, we can have any value, infinite number of values between two fixed points. When we work with quantitative values, we're going to usually display them as a histogram, which shows the frequency that we obtain specific values. All right? We can also exhibit it as a box and whiskers plot. So histogram is when we only have one group. So wing lengths of these roaches here in Cavernous. Wing lengths is one group. Right? Cavernous roaches, that's it. We express it as a histogram. We can see the distribution of our measurements. If we have two groups, so if we did the roaches here in Cavernous and the roaches in Science 3, then what we can do is display these data as a box and whiskers plot. We got more than one group. Each group has their own box and whiskers plot. It shows central tendency, dispersion, skew, outliers, and so forth. And we'll show you how to work with these next week, I think, is when we get to it. All right. Can we do the same thing with discrete variables? It's a little bit harder to do histograms because we're confined to whole numbers. All right? So with a histogram, it implies the continuous nature of our variable. But with discrete values, you can't really have a continuous line between 1 and 2 because you really don't have any of those intermediate values. So if we try to display discrete values, oftentimes we go back to doing frequency tables or possibly even bar graph where we say this percentage of individuals have this value. Okay? This percentage of individuals had 1 child or 2 childs or 3 childs or so forth. All right. Also with the variables, we have scales of measurement. All right. These are not mutually exclusive, all right, of the type. So our type is qualitative versus quantitative. All right. And then within these, we have a specific scale. All right. Our scale, those two, the types and the scale, allow us to pick out which tests we can run and which graphs we can make. Right.
So the scale and the type are not mutually exclusive, right?
Nope. So our qualitative data, those that are defined by attributes, can be either nominal or ordinal data. All right. So nominal and ordinal data are both variables that are in discrete state, expressed using their attributes and so forth. The difference between the two is that ordinal variables have a natural or implied ordering, whereas nominal data do not. Hair color. Is there an order to hair color? Is one hair color better than the other? No, there's no order to that. But you know, if I tell you to go out and check out, I don't know, Taco Bell, and I give you a cart that says, how did you enjoy your meal? And you've got 1 to 5 on there. Well, those are categories. You don't give me 1.5. It's 1, it was dissatisfied. 1, I was extremely satisfied. All of those points are categorical, but they have a natural or implied order. We've said 5 is the best, 1 is the worst. All right? So a qualitative can either have an order or they don't. All right? So if they don't have an order, they're a nominal variable. If they do have an order, then it's an ordinal variable. These ordinal variables are often called ranked variables, kind of because we've ranked things from best to worst. Our continuous variables are going to either be interval or ratio scales. And discrete as well, our discrete variables, I should say, our quantitative variables will be interval or ratio. All right? The difference between these two is, do we have a clearly defined 0 point or not? That's our difference. Do we have a 0 point or not? And it's not an arbitrary 0. It is a real 0. All right, so interval scales are all of those continuous variables that are on an arbitrary scale that lack a meaningful 0 point. Our range in this case can be negative infinity to positive infinity. What this means when we don't have that true 0 is that the difference between the numbers and units is equal over all levels. Right? Going from 5 to 10 still represents 5 units. Going from 10 to 15 represents 5 units. However, the ratios don't really make sense. All right? 5 out of 10, right? Yeah, that's half of that. 10 out of 20, that's half. But what about negative 5 compared to positive 10? What's our ratio? If we started at positive 10 degrees Celsius, and then at night we're down to negative 5 degrees Celsius, how much did our temperature drop? Well, we can give the actual number, it dropped 15 units, but we can't really give it a percentage and say, oh, it dropped by 50%. That ratio doesn't make sense because we don't have a 0 that kind of anchors our scale to a fixed point. Ratios do. All right, that's why we have the ratio scale. All right? It includes a meaningful 0. And now, not only are all of our points the same points, so 5 to 10, 10 to 20, now any ratio that we make or any proportion that we make now makes sense because we can't go below that 0. We don't have negatives. All right? So on our ratio scale, this is almost always continuous variables. The exception to this is the proportions. So if we convert all of our numbers to proportions, that's also a ratio scale because we're bounded by 0. We have a fixed 0 point. All right? So do you guys kind of get the difference between these two? All right, so what I want you to do is I have some practice. All right? Look through these values. We want to know the variable type in the scale, and what we'll do is we'll pick this up on Friday on this slide, and we'll go through and we'll say what type of variable it is and what the scales are. All right? So look at them, think about them, have some answers, and we'll pick this up on Friday. Don't forget homework. Yep. Need help on homework. All right, if you have questions about the homework, if you run into problems, please email me, contact me.